about blood is to learn about platelets. Now, some people call platelets thrombocytes because they have to do with clotting, thrombus formation, but they are not cells. So I don't want you to learn that word. So let's look at platelets. So to do that, we need to start with a picture of red bone marrow. So over here is red bone marrow. I've left bone on the left side of it. You can see compact bone on the left side. So this is red bone marrow. And I want to draw your attention to these larger cells that you can see. And here is a close-up picture of one of these larger cells. So this is a large cell that has a very large nucleus with a lot of parts to the large nucleus, like a lot of lobes to it. And so this cell has the name megakaryocyte, which means the cell with the really big nucleus, because that's what the cell is. And you can see how much bigger it is than all the other cells in the red bone marrow. Now, if we take this cell and we look at it even closer, you can see on the edges there are darker areas. And these darker areas are the areas that will break off and become platelets. So basically, the megakaryocyte is making certain things that will then coalesce on the edge, and then a fragment of that megakaryocyte will break off, and then you will have a platelet that contains these chemical things. So we don't need to know for this course what it is that the platelet contains. So a platelet is a megakaryocyte fragment, and your body makes 200 billion of these a day. All right, so how does that translate to how many are going to be in that little 1 cubic millimeter? So remember, we had 5 million red blood cells and we had 5 to 10,000 white blood cells. Well, we're going to have 250,000 platelets, okay? And so these are the tiny little cell fragments, and each platelet will circulate for about 7 to 10 days only, and then they are replaced. So platelets are responsible for blood clotting. Without platelets, you wouldn't have blood clotting because they are part of the first step and also part of triggering the second step of blood clotting. So blood clotting, if you cut yourself, you get a nosebleed, anything. In a normal person, that will take 5 to 6 minutes. So if you get a nosebleed and you hold your nose for 2 minutes, don't be surprised if your nose keeps on bleeding, because blood doesn't clot in anybody in 2 minutes, because it has these 3 steps that require 5 to 6 minutes. So the first step of blood clotting is when you cut a blood vessel, you nick a blood vessel. What happens is you are exposing the wall of that blood vessel, the collagen that is there. You're exposing that, and when the platelets come by, it causes them to change their shape and they become sticky. And so when the next platelet comes by and it hits a sticky platelet, then it changes its shape and it becomes sticky, and the next one, and next one, and next one. And so what happens is you get this whole soft little aggregate of these platelets that are sticky, and they form this very soft little platelet plug. Now notice this is only at the site of injury. Okay. So when they did their change in shape, they also were releasing chemicals, and there were also chemicals being released because the site of injury. And so I don't have to know the names of the chemicals. And these damaged tissues and the platelets release substances that start this coagulation cascade. So what coagulation cascade is, we have these proteins that are in our blood normally in an inactive state. And so a chemical comes along and it hits the first one and activates it. And when the first one's activated, it hits the second one and activates the second one, and the second one activates the third one, except that we do this backwards. Factor 12, when it's activated, activates factor 11. When it's activated, activates factor 9, et cetera, et cetera, et cetera. And there's actually several different ways that we can activate this coagulation cascade, this group of proteins that gets activated. But no matter how you get activating it, and there's this common final pathway. I do want to point out this one factor right here. It's called factor 8 because I'm going to be talking about it on the next slide. So the final common pathway is the third step in blood clotting, and that is this fibrinogen. Do you remember when I was talking about what was floating in blood and I was talking about the different types of proteins? One of the types of proteins I mentioned was fibrinogen. Well, fibrinogen, when it gets activated, forms something called fibrin. And what is going to happen is fibrin is going to form this meshwork that is going to trap red blood cells temporarily near the site of where this platelet plug was. And so we're going to have the platelet plug and we're going to have the fibrin mesh and we're going to trap red blood cells. And yes, of course, white blood cells will get trapped there. But like I said, this is temporary because if this wasn't temporary, then all of your blood would be clotting because as you can see, this is a positive feedback kind of thing that's happening. And so while this was being activated, some of the active things here actually activate other pathways, which are going to come along and start breaking down this pathway. And so what is going to happen after a certain amount of time? So stop and think. Have you ever um, skinned your knee or something and it's like it was dry so you wore shorts and then later on you notice like you had this yellow stuff leaking from it? That was the serum. Well, that was because the fibrin mesh was breaking down. Okay, the clot was breaking down, and so that is what has to happen before the tissue can start repairing. So those are the 3 steps of blood clotting. Make sure you know the platelet plug first, followed by coagulation cascade, followed by the fibrin mesh. All right. So let's go back to this factor 8, and that's involved with this disease called hemophilia. And hemophilia is an inherited clotting disorder. The most common one is a factor 8 deficiency. There is another factor that can be, but it's much less common. Factor 8 is a gene that's coded for on the X chromosome. So this is a sex-linked inheritance. If you remember, women have 2 X chromosomes. So you can have a deficiency of one and still have a normal level of factor 8 because the other X is coding for it normally. Whereas men with 1 X and 1 Y, if you have a deficiency on the X chromosome, you don't have a backup X. You're going to have the disease hemophilia. So women are carriers, but men get the disease. And this was a big problem in the 1800s and 1900s and all the royal families in Europe, in Greece, Prussia, and Russia. Why? Because back then people didn't marry for love. They married for political reasons. So there was a lot of intermarriage. Royalty only married royalty. You know, Queen Elizabeth married royalty from Greece. Okay, so with hemophilia, so go back to this. If you don't have factor 8, that means you can't go down here and you can't form your fibrin mesh. So you can't form a clot. All right. So if you can't clot your blood, you're going to bleed. So with a factor 8 deficiency, the slightest bump leads to bleeding. And if you have a factor 8 deficiency, you usually die in bleeding, usually due to a brain bleed from the slightest bump on the head that would go unnoticed in the rest of us. And nowadays, we can prevent that with regular factor VIII injections to keep factor VIII levels normal in men, well, and boys, obviously. So if we look at all the royal families at the time, okay, all the squares are men and the circles are women. And so in order for the man to have the disease, his mother had to be a carrier because it's an X-linked disease. Okay. So notice the men with the diseases are dying off before they're having offspring. Yes, because that's what happened back then. Factor VIII for injection only happened in the last since the 1980s, from around the time of HIV, because factor VIII injections in hemophiliacs. This is why hemophiliacs were one of the biggest subgroups of having HIV/AIDS at the beginning. Okay, so when we look at who had all the royal families die off, the Spanish royal family died off because, back then it had to be carried by male heirs. Okay, the Belgian royal family died off, the Russian royal family died off, the Prussian royal family died off, but you notice we still have a British royal family. That's because none of them have hemophilia. But here's what's very interesting. If you trace royalty going back, the person with the gene can all be traced back to Queen Victoria of England. Okay. So her son Leopold lived long enough to have a child, a daughter, to pass it on to the Belgian royal family. But after that, it was her daughters that carried the genes to give it to the Prussians, the Russians, and the Spanish. And her children that went to the British royal family, none of them carried the gene. All right, that's it. And so come on back as we continue a brand new topic next time. And thank you so much for all your hard work. I really, really